Ready to go with cyclohexane chair conformations online lesson. Please refer to your packet. If you have lost one, you can go on to Blackboard under content. The appropriately named file is C201 202 cyclohexane chair online lesson packet. Okay, so we'll show you a lesson. This is from chapter 4, which held in it alkane IUPAC nomenclature, such as 6-methyl dodecane. And it also had in it cycloalkane nomenclature, such as 1-ethyl, 3-N-propyl, alphabetizing, cyclopentane. And it had in it, we discussed relative stabilities of rings. That's where we jumped ahead to chapter 5 and had to leave go at the time discussions of cyclohexane, the most stable ring. Cyclohexane doesn't even know it's in a ring. So in other words, if you burn 1 mole of hexane, C6H14, and you burn 1 mole of cyclohexane, C6H12, normalizing the number of carbon-hydrogen bonds, the energy content for the heat released is the same. That is not the case if you burn cyclopropane, looks like a triangle, and if you burn propane, C3H8, the other one was C3H6, burn both of those. It's going to be, if you normalize things, cyclopropane, which is releasing more heat because of the ring strain. So it may seem odd to you that we have 3 sections, 4 sections more, 5 sections in a textbook dedicated to just 1 molecule, cyclohexane, but that's the case because this molecule is prevalent with respect to biochemistry. Chitin, the stuff of crab shells, cellulose, the stuff of dead leaf litter, biochemistry related. If you have this is all monosaccharides and linking up into polysaccharides, where rather than having 6 carbon atoms in these saccharides, such as chitin or cellulose, there are 5 carbons, not 6, and the other atom is an oxygen. And so that's what makes these cyclohexane conformations important, is because monosaccharides and polysaccharides assume the same shape, which is a chair conformation. We're ready to go here. Here's cyclohexane. You can see it, C6H14 overhead view. Looking down at the ring. And here we have cyclohexane edge-on view. All right, and this is hopefully you'll keep that out, and you'll keep that paper out. Here comes a modest demonstration. The peg-chipped carbons are represented by the blue plastic pieces. So this is sure enough a 6-membered ring, and the peg-chipped carbons, let them be represented by the blue plastic pieces. Like on the handout, I'm doing this live for you. You can arrest this carbon, this hand don't move, and then with this hand here, you can swing this carbon upward, and that's going to deliver what's called a half chair. A half a chair. And for the other carbon I had arrested, now we can pivot that away, down, and now we have a chair conformation. It's like a lounge chair. Here's a pen. If I do this right, the pen can rest in the chair. The headrest is over here, pillow and stuff, And down here is the footrest where the sandals are, down here, footrest. Headrest, footrest. It's called headrest because isn't this higher in altitude? It's higher in altitude. So this is called the headrest. H, headrest, H, higher in altitude. So what I just showed you is this business. Okay. It's that business. So how this will go is we'll want to get good at drawing respectable chair conformations. You have to have a certain shape, and I'll let you know about that. After that, we'll do some exercises about which conformation is the shape is the conformation, shape conformation, same word. Which shape or which conformation of a branched cyclohexane is most stable? So the next paper, I'm sorry, I'm going to treat these in a different order. So if you can hang with this and skip ahead to this page. Sorry, I guess when I put all this together, I thought I was going to cover it, then I'll change my mind, if I may. I'd like to show you what constitutes a good chair shape and a not so good chair shape. And fair or not fair, another chemist can judge a student based on how they do two things. First, how they answer this question. True or false, alcohols can undergo SN2 reactions. False. So answer false to that one. And the second thing is someone gives you a piece of paper and a pencil, says, okay, draw me a chair conformation. Go ahead. So this is two ways where people can form quick judgments about how good of a student someone is in organic chemistry. So hopefully you would perform well and reflect on yourself well with both. So let's see the scouting report. As I said, I skipped a few pages ahead. What makes a good quality chair is this chair has, with 6 vertexes, has an up, down, up nature. The peg-chipped footrest, if I may abbreviate footrest, and the peg-chipped headrest are so indicated. What you don't want to do, because it's going to mess up these bonds called axial and equatorial bonds, what you don't want to do is have a cyclohexane chair conformation, which has a level type of bond to it. So what we need is up, down, or down, up, down. We do not want any level bonds. It has been said by others that cyclohexane chair conformations resemble a certain domestic beer company's logo. Can you think of it? The second aspect of cyclohexane chair conformations, which makes them good, is that they're not pinched. This is I don't know how else to put it. This is a pinched chair conformation. So you see what's good on the left, what's not good on the right. If you were to operate with a pinched chair conformation, that would lead to difficulties inputting axial and equatorial bonds and throw everything off. And lastly, cyclo, I just said it, axial is to AX, equatorial is to EQ. So this comes from the Earth. I'll write E here for Earth, if I may. So the Earth has an axis, North Pole, South Pole, and it has an equator. So likewise, I can axial bonds are up, equatorial bonds are down. And this is like eating French fries with mayonnaise. Ever see that? I think they do that in Belgium, but this is terrible here. This hurts my eyes, seeing a cyclohexane chair conformation with wedges and hashes. Okay, so that's really, please, I beg you, don't do that. Okay, so you will never see a cyclohexane chair conformation with wedges and hashes. So I don't want you to do that. I want you to look good. So don't do that. And do you remember the a little do you remember the vertex rule? If the vertex points up, the bond points up, the vertex points down, the bond points down. That is in keeping with the axial. The vertex rule is in keeping with the axial bond positions. If you imagine a little green car, and this green car is on a road, and this road is heading down, that means you have to use your brake, otherwise you'll go too fast down the hill. Then, therefore, if that car is going downhill, then the axial is going to point down. So this, again, if I had a green car and this car was here, let's say, looks like I have to make a car here, and that car was going uphill. So therefore the vertex points up and the axial will point up. So I'm putting in all the axial bonds. Axial. Axial, guys, is straight up or straight down. The axial position is 100% fully up or 100% fully down. Vertex points down, axial points down. Vertex points up, axial points up. If you would like me to do this, please forgive me if you don't need this, but what if we have another green car here, and this green car was heading uphill, is it not? On its Sunday outing, it's heading uphill. Therefore, the vertex points up, and the axial will point up. So you see the necessity of having up, down, up, because if you had a level bond, then how would you know if axial points up or axial points down? And so you should be, if you're taking notes, you should say axial is 100% up or 100% down. Equatorial, an equatorial bond is partly up or partly down. So it depends on the axial. So I've tried to remind you, the alphabet can help you remember the order of things. Back when we were discussing carbocations, I had advocated try to do a hydride shift first before you do an alkyl shift. H becomes before R in the alphabet. As such, doesn't A come before E in the alphabet? So therefore, we'll want to input axial bonds first, quickly, and then we'll put equatorial bonds after axial. So since this axial bond here points 100% fully down, axial down, therefore the equatorial will point partly up. That's the story, as to be fleshed out in future pages here. Here we have an axial which is 100% straight up, and to answer that, the equatorial, to try to balance this out, the equatorial will be partly down, will be modestly down. And partly up, just barely up, because the axial is fully down. So more to come on that, but I have a full page dedicated to that. But first, I want you to get good at drawing chair conformations. So if you can scroll back up with me or turn the pages up ahead. So we need up, down, up vertexes. We're going to draw some chair conformations here. We need an up, down, up vertex. Not registering. No level bonds. We need sharp vertexes. straight bonds, and no pinch chairs. And more? Well, let's see. I would recommend drawing chairs freehand. I'll do my best. I usually like to do this with a pencil and paper. I'm at a disadvantage here because I have to use a mouse. I will do the best I can. Otherwise, it just gets to be too tricky with delivery systems going from the marker board to this, and it's just too much. Okay, so I will try to emulate this. I'm taking it slow. Not back all the way. I missed that. That's my first attempt. Try again. I like that. If my hand wasn't so shaky, that'd be great. Yeah. What I have a knack of doing is doing this bond first. Okay, so I know your handout shows you like do that, but if you, I just can't. It's just habit on my part, just doing that bond first. See that bond I just drew? That bond and the bond across from it should have the same mathematical slope of a line if all goes well. Chairs are not pinched. Remember, this is not a good chair here. It's level bond. Oh no. Oh no. That's a level bond. Not good. This is a pinched chair here. Pinched chair. Not good. I'll try the ones below. So when I do this, actually, I found out just like delivering this, I make that bond first. So I just, you don't have to make that bond first. That's just how I do it. And you're probably going to find like you're going to be able to make one chair a little bit better than the other chair. We're making chairs here where the headrest or the highest position is to the left. They'll have different qualities. Yeah. I like a little bit more separation here between the upper bond and lower bond. So I'm going to make that bond a little bit higher and come back a bit. Okay. All right, I'm going to hold here for, I have a watch on, so I'm going to hold here for a minute and a half. And it's to you guys now, okay? I want you to take this time, pick up a pencil and practice some chair conformations. It should be up, down, up. They should not be pinched. Go ahead, I'm timing this. It's time to move ahead. I'm sorry when I went to the copier, I did not hit the right button, so yours came out grayscale. But here we have one of these flat chairs. Remember how I started out this circuit? I showed you a flat chair. you guys, this model wants to make a chair, and I'm trying to tell it not to. Okay? That's how stable the chair like I keep trying to make this flat, and the plastic bonds keep wanting to do this spontaneously. So that just shows you the stability of a chair conformation. More to come on that. So like we started out earlier, this is a flat cyclohexane chair conformation, and so we're going to pivot one end up and one end down, making a chair. I'm now touching the headrest. This is the footrest is over here, footrest. So we're representing that, and here's the formal definition, everybody, for axial bonds and equatorial bonds. So axial bonds in green here. I think yours show up as a different shade of gray, so they are representable as I look at it now. They're representable. Perfectly vertical, axial, straight up or straight down. It's an extension of the vertex rule. You remember the vertex rule from chapter 1? It's the very same. And here we have equatorial bonds, and the rule is if the axial, like in Seinfeld, things have a way of evening out. So if the axial is straight up, the equatorial answers by being partly down. And if the axial straight down, the equatorial answers by being partly up. So things have a way of evening out, partly anyway. By the way, if you maybe encountered some trouble drawing chair conformations, there is a saving grace called the M and W method. So what you want to do is you want to make a kind of a wide M and a wide W, but how I did it here is not correct. No, because you have to offset the M and the W. The M has to be a little bit ahead, or the W has to be a little bit ahead. This is ready to go. That's ready. And then you notch the interior carbons like this, and then there you have a good chair conformation. Hopefully you're working in pencil, because you're actually gifted some equatorial bonds here. So to have a good chair conformation, it should not have any loose edges. Back when I was taught at Slippery Rock University, we didn't have any overhead projectors or televisions in our room. It was just chalkboards back then. So the instructor I had, she taught the classic technique where, like the M&W method, she had two offset lines, and then she put C's there and in the gap spaces and tried to close the C's. So this method is kind of more ancient, but you can still, but that's how some textbooks still advocate like that. And here is just a formalism about drawing axial and equatorial. So as I said, I tried to demonstrate this earlier. I took time to say, what if there's a car on the road, the car is driving downhill, the vertex is down, the axial is 100% straight, fully down. And here we see an instance of where you're driving uphill, where those gray arrows are, that this axial bond is up. And if the axial points straight up, the equatorial points partly down, as nicely labeled there. Now we're going to skip this page. I think it'll be more instructive to go to the next page. I talked about that page. Doing pretty good, aren't we? Here's a very instructive thing here. I'm looking forward to doing this handout with you. Okay, so number 1 on this recitation sheet, identify by name the shape each cycloalkane assumes. Cycloalkanes can have torsional strain due to eclipsed bonds, electron-electron repulsions, or ring strain. The angles are too pinched. So in order to relieve some of that pent-up energy or that strain, a square cyclobutane will change shape into a butterfly conformation. I believe I showed you that one day. A cyclopentane conformation will assume an envelope conformation, which appears like a wave going around a baseball stadium, where that raised vertex is only one of them, undulates around the circumference of the ring. Cyclohexanes, what shape are they? Chair conformations. True or false? It's underlined false. Oh, it tries to trick you at times. Oh, no, 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 no. Never, never will cyclohexane be shown with wedges or hashes. So this is a very instructive exercise here. It's not too late for me to zoom this in. Input axial or equatorial bonds. Input and label axial bonds, excuse me, for the pegged carbon atom. So I'll give you a chance to work ahead if you like. So those are your instructions. Recall if the vertex points up, a timely reminder, the axial points up, and if the vertex points down, the axial points down. So go ahead and if you want to try, if not, I'll work on it in just a bit. See what's ahead here. Okay, let's go. So this vertex is pointing down, the axial points down. Please make that 100% fully down. So I'm going to do this even. There I go. That's more like it. And this vertex points up, the axial points up there. Axial points up here. Remember the car, right? The vertex points up, axial points up. This one here, if I pretended I had a car here, and that car is driving toward the peg chip, that car will be going downhill, down, axial points down, just like that. And if you have your wits about you, have a little break here. Okay, so I'm gonna see if I can zoom this in here, and then find where I am. We have to have, oh, I did it. See a little break there because this bond is in the back. Okay, this bond is in the back. Stop share. So look where my finger is. It's hard to see my finger because there's a bond in front of it, right? So it's much the same story. We're talking about an axial bond in the back. There's something in the way of my view. So that is why there's it. If you can manage it, it would look really nice if you can have a little bit of a break there. See how I broke it? I was lucky there because I did that at 100% magnification. Now 680% magnification, it passes muster. Zooming out again. Axial. And these chair conformations here, an additional question, can you find the headrest? This is the headrest here. Headrest. The headrest is either the very, 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 very leftmost or very, 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 very rightmost carbon, which is up. Here, this is the very leftmost carbon, which is up. This is the very, 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 very leftmost carbon, but it's down. Aha, so that's a footrest. This is the very, 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 very rightmost carbon, and that's up. That's the headrest. This is the headrest carbon here, coincident with the one we did. This is the very, 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 very leftmost carbon, and it's down. That's a footrest. This is the headrest. So I just open circled the headrests in case you were curious. Let's zoom in. And now we're supposed to, on this very clever handout that I made of my own design, now we're supposed to input equatorial bonds. If you remember, we have to put the axial in first and then put the equatorial in last. Let's just go across here and put in the axial. So you have a little break there because that's in the back. So if you will, this is in the front, more toward you, down, down. And it just stands to reason that if axial is down, equatorial is partly up, and if axial is up, equatorial is partly down. So the green arrows represent equatorials. In this case, it doesn't matter if you shift this to the left or right. I'm going to put it partly up. This is incorrect. Okay. Oh no, don't do that. So this is okay. Good to go. This is okay. Good to go. Here, the next one, axial is up, equatorial is partly down. Getting the hang of it. Oh, looks like I did one wrong here, didn't I? Oh, please forgive me. Hmm, too late to get rid of that. Oh, I made a mistake. I didn't even mean to make one. Hmm. I did the other two okay. Yeah. And axial's down, equator's partly up, partly up. Oh, that's how you get rid of that. Okay, great. Let's help me out here, Arrow. Come on, let's go. This is too steep. No, no, that's not good. This is level. That's not good. Okay? That's not correct. Equatorial is not level. Equatorial has to make up its mind. It wants to go to Burger King or McDonald's. You can't say both. You have to pick one, up or down, Burger King or McDonald's. So it has to be one or the other. Correct that. So please forgive me. I didn't mean to make a mistake, but I am human. So and I can so axial is up, therefore equator is partly down. And you can swing it this way. And by the way, guys, you should connect this to the vertex, please. Okay. Thank you. It's kind of hard to present things by computer sometimes. I'm sorry. Or you can swing it that way, like that. And so you see the utility of having an up, down, up cyclohexane chair conformation. Because if we had a level bond, we wouldn't be able to make up our mind if axial points up or down, and what happens to equatorial. So, I hope you're learning a few things about chair conformations. And we'll have to remember, perhaps, if you do, if you don't, that's okay. On future worksheets, we're going to be reconciling the wedge hash nature of a polygonal structure with the chair conformation. So wedges to up, hashes to down. I always think that, look how close. Look how close U and V are in the alphabet, right? So up is to wedge. Look how close U and W are in the alphabet. So up is to wedge. Here's an important point. For cyclohexane rings, which have one branch, maybe ethyl cyclohexane or isopropyl cyclohexane or N-butyl cyclohexane or methyl cyclohexane, all things being equal, a bulky substituent is placed equatorially. That's the best place for it. It's more roomy there. More room for a bulky substituent to be placed equatorially along the equator than to be placed axially. Proof, please. I place this group equatorially. It's out away. Lot of free space here. It's out away. I place now this group axially. This is crowned with hydrogens. Not much room here. I'm hitting the top of my fingers. I'm hitting my palm. Too much for my liking. A lot of sterics. Whereas if I detach axial and place equatorial, not a problem. This can torque any way it likes to in open space. It's like having your own armrest on an airplane. Isn't that nice? Equatorial is better. Okay, this one asks you to trace some cyclohexane chair conformations. You did that earlier. Let's skip ahead. For the record, the most unstable is bad, and this isn't bad, okay? This isn't like, this is like, if you want to nitpick, at a chair conformation, this is what you would address the chair conformation as being short of. There are destabilizing, that's bad. 1, 3, 1 axial, 3 axial, or 1, 3 diaxial interactions. They're destabilizing. There's carbon 1 in the chain, carbon 2, carbon 3. I can number them if you like. But that's as bad as it gets for a chair conformation. Carbon 1 of the, excuse me, I just said chain. Please swap that to ring. So 1, 2, 3, carbon 1, carbon 2, carbon 3. So these axials are just kind of getting in each other's way, okay? And the symbol we use for that is 2 interpenetrating parentheses that represents sterics, okay? 2 interpenetrating parentheses represents sterics. So, but that's they're at least they're you know they're not neighbors, you know, they're a little bit apart. The 1, 3 diaxial. And also we're saying here that these bonds, providing they're bulky, like if these were 2 ethyl groups, then they would be getting in each other's way to an extent. But that's as bad as it gets. So there is no ring strain. There is no torsional strain. That's why this is in a chair conformation. Chair conformations remove torsional strain attributable to eclipse bonds, causing bonding electron intramolecular repulsions. I'll bring that up in a minute. You can hit pause too. What this is saying is, again, this is flat. And again, I'm having trouble making this flat because this plastic piece wants to assume a chair conformation, and I don't want it to do that for demonstration purposes. That just shows you how stable a chair conformation is. Still trying to do it. You're having a tough time seeing this. You're having a tough time seeing this bond in blue now, aren't you? You're having a tough time with that. These bonds here I'm touching with my fingers are eclipsed. They are eclipsed. As such, these electrons are wanting to repel from each other. They're trying to get away from each other because they're coulombics, electron-electron repulsion. So if you were to strike this as a chair, now we don't have that problem anymore. Now the bonds are not eclipsed if we have a chair conformation. This is the bond. These are the bonds that we were formerly worried about. They are not anywhere near eclipse. This is called gauche. The bond angle is 60 degrees. 60 degrees, 60. Hold up here. Oh, sorry. Got it. Got it. Got it. 60 degrees. Gauche. It's not eclipsed anymore. 60 degrees. Not eclipsed anymore. 60 degrees. Short of 90, 60 degrees. That are not eclipsed anymore. And that's why share conformations are prevalent in nature, because there is in a chair conformation, there is no ring, there is no angle strain, and there is no torsional strain due to bond eclipsing. In a flat cyclohexane ring, there would have been torsional strain due to eclipsed bonds. That's why that plastic model was wanting to assume a chair conformation even before I was ready to take it into one. The information is in the geometrics, how they make them at the factory, chair conformations. So this was an edge-on view if all bonds are eclipsed. And believe me, this took me some time to draw this on ChemDraw. And if you did the ChemDraw assignment, you know, maybe you know what I'm talking about. These bonds are eclipsed, 1, 2 eclipsed. In a flat polygonal ring, all bonds are eclipsed. And on the next page, please. I was about to say checking for questions, but I'm teaching on. All right, so monosubstituted rings, redraw the overhead projection as a chair conformation, conserving the wedge hash spatial information. So recall, wedge is to up, hash is to down. So I have a hash. So somehow I have to, the bromine needs to be down. So we have to remember what we have about axial and equatorial, okay? At this particular peg chip, the axial is straight up and the equatorial is partly down. One's up, one's down. All right, so it looks like we're going to station the bromine equatorially. Bromine needs to be down. What about this one? Oh, if you leave that go and move on, that's going to be incorrect because that's a methyl group, CH3, unless and until we put a capital H there. Now it becomes a hydrogen. Clear. Good. Moving on. This is still a hash. The answer here will be the same. I believe it's the same answer. Axial straight up at this particular vertex peg chipped. Equatorial is partly down. I have a hash bond. It doesn't matter to me if the hash bond is going northeast or east or southwest. It matters to me that the hash is a hash is a hash. A hash means down. Pencil in bromine down. And I want to make sure this is a hydrogen here. Here comes another opportunity. A bromine, I'll type this for you. This is a wedge. Wedge is to up. Need bromine up. But this axial vertex rule points down. Remember the car analogy? And so if the axial points down, the equatorial points partly up. Please connect that to the vertex indeed. I'm trying. I think I'll have to try again. That's a lot better. Thank you. And I will now pencil in bromine up, partly at least, and hydrogen down. Same game here. Same peg chip. This time, bromine is on a hash. Hash is to down. Input the axial equatorial positions. Decide which one's up. This is up. This is down. How do I know that? Because place your pencil on the ring carbon. Trace the axial straight up or straight down. So your frame of reference is the ring carbon. And if I have bromine down, that means I need to have a bromine here. And this makes this H. Next page, this may be it for this parcel of the assignment. So I want to take this all in one and at one, or else it's like going to a smorgasbord and eating too much, and then you feel sick, you know. So this will probably be the last one for this skit. Rewrite each mono-substituted ring, and we're going to draw a chair here, and a chair conformation while conserving the wedge or hash. Okay. All right, so let's draw a chair. I'm going to draw a chair like this. I will do my best. Up, down, up. Striving to improve upon my last chair. Oh, I like that one better. I want to use that one. Okay. I like that one. Yeah, either of them are good. Because if I was to do the axial here, nothing would be in my way. If I was to do the axial here, nothing would be in my way. That would be straight down. So they're both serviceable, but I would like to use that one. Most stable. Do you know where this is going? You remember that one page? It says all things being equal, for a bulky group, it is best to place it. Remember me talking about armrests on an airplane? All things being equal, it's best to place the group what? Axial or equatorial? The answer is equatorial. No, we're free to, nice to have freedom to pick any carbon you like on the ring. I'm for that. I guess I'll pick this one because I have more room here to operate. So yeah, otherwise it's going to be jammed up against the given molecules. And it doesn't matter which one you pick. In other words, there's more than one way to solve this problem. So from this position, there's the axial, and from this position, here's the equatorial. There's no rhyme or reason why I'm drawing that with an arrow or red or green. So just using different representations. So you should not draw equatorial with arrows if it's not too late. Yeah, so we have to draw here what we have here before us. What type of alkyl group is this? Well, it's a 4-carbon alkyl group, so I'm thinking N-butyl, or I don't think so. T-butyl? No, I recognize that. S-butyl? Isobutyl? That's it, because you have that little triangle end cap. Does this thing have a triangle in it? No, it doesn't. There's a polygon. Oh, all right. Whoops. Cinch it. double click. Yeah, so it has that. This is an isobutyl group. Whoops. Thank you. It's a free square for you. And well, yeah, no, this is not bingo. And now I wanted to remember that this is a hash bond, and this is going to be down. Hash bond is down. So on the particular carbon I picked, that's C. This is down. This is up. Blast. I need it to be on an equatorial, and I need it to be down. Well, let's try this one. And what I'm going to make for you in so doing here is a construct you can use each and every time. You didn't know that, did you? So I will now put some labels here. Axial down. Do you need it? Nope. This is equatorial up. Do we need it this time? No. This is equatorial down. Do we need it? This is it. This is axial up. All things being equal, it's best to place the alkyl group equatorially and in keeping with the hash down. So the answer, substituting in like with a formula in the math class. Oh, I don't like that chair. It's the slope was too steep. From here, draw. It needs to be this bond angle. You need that bond angle. From this, isobutyl, please. 1 carbon, 2 carbon, like that. Also acceptable. Oh, sorry about that. If you can let go of that non-sharp vertex, I would appreciate it. Thank you. That's good too. All I'm looking at is this bond here. That's it. That bond off the first bond off the chair is partly down. Got it. Isobutyl, 4 carbons. Good. Let's try another one where you have some more space. And this is your formula. Solve these. I can make that into a handout if I wanted to. It's that important. Try not to wander too far away. And also try to give myself a place to do another example here. So, ready. Let's try this one with the ethyl group. We're looking at G, most unstable. Oh, we got to read carefully there. Whew. Just in the nick of time there. I did the most stable here. So most unstable, that means axial. That means I would want to have this group axially. Have it most unstable. Axial, wedge means up. Where do you on that boxed formula find axial up? Axial up. There you go. You put it there. How are your chairs looking? Up, down, up. No level bonds. No pinched chairs. Ethyl up. That's the same molecule. Wedges up. Most unstable shape. That's it. Because you have the 1,3 diaxial interactions. Most stable would be wedges to up. There, I'm kind of locked into this mouse here. So wedges to up. Remember how close they are in the alphabet? Draw another nice chair. What do I need here? Wedges to up, most stable. That's, I'm thinking equatorial. Put them together, equatorial up in this puzzle. Equatorial and up. Can you find it? Equatorial, there it is. What do we need here? Chlorine? Chlorine. Chloro. That's cyclohexane, excuse me. Oh, good for us. we'll see if we want to take this any further, but now you know more about chairs. You know, a great majority of chair conformations, their permutations. We'll see if we want to have a 20-minute follow-up to this or not. And thank you very much. I hope you took something from it, and we'll see whether or not we get a homework assignment. Keep up all the good work. It'll pay off. Have a good one.